These next two examples are going to be examples of using the chain rule with trigonometric functions. So let's differentiate y equals cosine of 7 to the x. If you look at this, the fundamental operation occurring is composition, and that's because to figure out what this answer would be, we would first compute 7 to the x, and then our very last step would be to take 7 to the x and input it into the cosine function. So that tells us that our inner function is 7 to the x, and that's what we make u. Okay, 7 to the x is our u. And that was our inner function, so to figure out our outer function, we rewrite the original y equals cosine of 7x, and everywhere we wrote 7x before, we're going to write u. And so now, we want to take our inner and outer functions and go ahead and compute, went too soon, jumped the gun, dy du, which is negative sine of u, and also du dx, which is 7 to the x times the natural log of 7. So our chain rule tells us dy dx equals dy du times du dx. We can do this in two smaller stages. Okay, so dy du is negative sine of u times, and then we need to multiply it by du dx. And now we're going to substitute in, instead of u, we're going to write 7 to the x. Instead of du dx, we're going to write 7 to the x times natural log of 7. So we get negative sine of 7 to the x times natural log of 7 times 7 to the x. And that's our final answer. Let's do another one. Let's differentiate y equals sine squared theta. Now here's a concept check for you. What does sine squared theta mean? Is it sine times theta? Is it sine of theta? Is it sine of theta squared? Or is it sine of theta squared? Notice I said the same thing with each of these last two, but they mean something different. Do I take sine of theta and then square it? Or do I square theta and then take sine of that answer? Okay, think about it for yourself. And sine squared theta actually means the C answer. You compute sine of theta and square it. That's just notationally what it means. I don't have a good answer for why it's written that way, other than if you had to write sine of theta and then square it, it gets cumbersome with the parentheses there. So, now that we know what it means, we can go ahead and work on differentiating it. So let's differentiate sine squared theta, which is, of course, sine of theta, all of that squared. So if we are taking the derivative here, this is a composition of functions. Here we would figure out what sine of theta was first, and then we would take that answer and we would square it. So that tells us our inner function, u, is equal to sine of theta. And du d theta equals cosine of theta. The derivative of sine of theta is cosine of theta. Y, our function, equals sine of theta, quantity squared. And we substitute in u for sine of theta and get that our outer function is y equals u squared. And so dy du is 2u. So to compute our derivative, dy d theta equals dy du times du d theta. So we substitute in dy du, and we get 2u times du d theta. And then we don't want u's in our answer, we want theta's in our answer. So instead of 2u, we're going to write 2 sine of theta. That's what u is equal to. And du d theta is cosine of theta. So our answer is 2 sine theta times cosine of theta. Okay. So notice that this is actually one that you could have done previously without the chain rule. Anybody know how to do it? Think about it for a second before I tell you. We could have written this as y equals sine theta times sine theta, and then you could have used the product rule. So y prime would have been cosine theta sine theta plus sine theta cosine theta. And of course we have written the same thing twice because multiplication is commutative, so we end up with 2 sine theta cosine theta. So it does not matter how exactly you take the derivative, whether you rewrite this a different way and use the product rule or you use the chain rule. It doesn't matter. You should arrive at the same answer no matter what.